Hey everyone, welcome back to the channel. Today we are diving into Hess's law, a key concept in A-level chemistry that's going to make your life a lot easier when you're working with enthalpy changes. By the end of this video, you will not only understand Hess's law, but you will also be able to confidently apply it to your exam question. So let's get started. Alright, first thing first, what is Hess's law? It's all about energy change in a chemical reaction. Hess's law states that the total enthalpy change for a reaction is the same, no matter which route you take, as long as you start and finish at the same condition. Think of it like going into a road trip. Whether you take the highway or the scenic back roads, the distance between your start and end point remains the same. For example, let's take some reactant and turn them into products. We might go through one direct path, or you could actually go through several intermediate steps. No matter which route you choose, the total energy change, the enthalpy change, is the same. Note here that we have two routes. Each route is decided based on the direction of arrows. So route 2, for example, here are the two steps that have the same direction of the arrow, while route 1 is a direct route from reactant to product. Here, route 1 will equal route 2, which means the enthalpy change of route 1 will equal the total enthalpy change of the two steps of route 2. Now, there are different types of enthalpy changes you need to be familiar with and understanding. This is to understand which are crucial when building our Hess cycle. So let's quickly review. First one is the standard enthalpy of formation, and this is the enthalpy change when 1 mole of a compound is formed from its element in their standard state. For example, making ethanol from carbon, hydrogen, and oxygen. Standard enthalpy of combustion. This is when 1 mole of a substance is completely burned in oxygen, like burning ethene to produce carbon dioxide and water. And there is the standard enthalpy of a reaction. This measures the difference between the enthalpy of products and reactant, usually under constant pressure. Let's now dive deeper into the Hess cycle. So now let's build a Hess cycle using the standard enthalpy of formation. Imagine we are looking at a reaction between sulfur dioxide and hydrogen sulfide, producing sulfur and water. We can break this reaction down into two routes. The first route is the direct route. The second route is the route when we use the formation of both the reactant and the product from their respective elements. So now look at the two different routes, and now you can decide these routes based on the direction of the arrows. So now we have route 1, which includes the two arrows which go in the same direction, the red one, and route 2, which is in blue, which goes in the opposite direction. In this example, route 1 will equal the total enthalpy change of the reaction and the enthalpy change of formation of the both reactant, the sulfur dioxide and hydrogen sulfide. Note here that 2 moles of hydrogen sulfide are included in this reaction, so we multiply the enthalpy of formation of hydrogen sulfide times 2 because there are 2 moles. Route 2, on the other hand, will have 3 of the enthalpy of formation of water because there are 3 moles of water. Note that sulfur is an element and the enthalpy of formation of elements equal 0. Now we apply the law of Hess. So the law states that route 1 will equal route 2. Now you need to add all the enthalpy changes on route 1 and route 2. Rearrange your equation to find the missing enthalpy change. Now let's practice. It's your turn to practice now. Here is a reaction between aluminum oxide, which reacts with magnesium to produce aluminum and magnesium oxide. Use the Hess's law and the enthalpy of formation values to calculate the enthalpy of this reaction. You can pause the video and give it a try yourself before you check the answer. Now, are you ready? Let's check the solution together. So now let's build the Hess cycle using the formation of both reactants and products from their respective elements. This is the first arrow, which we form the reactant from the elements, and then this is the second one where we form the products from their respective elements. And now you need to note the roots. So root 1 will include the first step, which is the direct step from reactant to product, and also the formation of the reactant from their elements. Route 2 is the one which has the opposite direction of the arrow, which conclude the enthalpy formation of the product. Now let's calculate the different values. So this is the enthalpy formation of aluminum oxide. Remember that magnesium is an element, the enthalpy of formation equals 0, and this is in addition to the enthalpy of the reaction. Root 2 will include 3 times the enthalpy of formation of magnesium oxide, because magnesium oxide there are 3 moles that have been formed, and aluminium is an element, so the enthalpy of formation equals 0. Root 1 will equal root 2, so now you need to put the values and rearrange your equation to find the enthalpy of the reaction, which is going to be minus 130 kilojoule per mole. We can also build the Hess cycle using the enthalpy of combustion. So imagine this reaction where we're looking at the formation of ethanol from carbon, hydrogen, and oxygen. Once again, we can break it down into two routes: direct formation and combustion steps for all the elements that are involved in this reaction. So the first combustion will be the combustion of the reactant to give carbon dioxide and water, and the second one will be the combustion of the product to give carbon dioxide and water. Now note the routes. Route 1 will follow the arrows. So route 1 will include the formation of ethanol and the combustion of ethanol, while route 2, the one in red, the one that has the opposite direction, that will only have the combustion of the reactant carbon, hydrogen, and oxygen. So now route 1 will be the formation enthalpy formation of ethanol plus the enthalpy of combustion of ethanol. Route 2 will be 3 of the enthalpy of combustion of hydrogen, because there are 3 moles of hydrogen, and 2 of the combustion of carbon, because there are 2 moles of carbon, and of course oxygen will not have any combustion in this reaction. Root 1 will equal root 2, and then you can put all the values and do your rearrangement to find the missing enthalpy change. Now let's practice using the enthalpy of combustion. So can you calculate the enthalpy of this hydrogenation reaction when you hydrogenate ethene to give ethane using this table, which gives you the enthalpy of combustion of the different reactant and product. You can pause this video and you can give it a try yourself before we actually look at the answer. Now let's answer this one. So first of all, we need to build our cycle using the enthalpy of the combustion. So first one is the combustion of ethene and hydrogen to give carbon dioxide and water. The second one will be the combustion of ethane to give also carbon dioxide and water. Now look at your routes. Route 1 will be the 2 arrows in blue, which are in the same direction, and route 2 will be the arrow on the opposite direction in red. Route 1 will include the enthalpy for the reaction or for the hydrogenation plus the enthalpy of combustion of ethane. Route 2 will include the enthalpy of combustion of both the ethene and also the combustion of hydrogen. Now route 1 will equal route 2. You can put your equation and then you can rearrange it and put the values to get the enthalpy of the hydrogenation, which will equal minus 126 kilojoule per mole. Now there's a quick tip before we wrap up. When you're working through Hess's cycle, if you flip an arrow, If you flip an arrow, or if meaning if you reverse the direction of a reaction, don't forget to change the sign of the enthalpy change. So look at this working example we just had a few seconds ago. And now what I'm going to do, I'm going to flip the arrow for this combustion reaction. When I do this, now the enthalpy is going to be, we're going to change the sign of the enthalpy change for this particular step. And now instead of using the enthalpy of combustion of minus 1560 for ethane, we're going to use the minus of that value. So it's going to be plus 1560 kilojoule per mole. Now note that there has been a change now in the roots, so follow the arrows to find root 1 and root 2 and the different enthalpy changes for both roots. You can do your rearrangement and then you're going to get the exact same value for the enthalpy change of the hydrogenation of ethene. That's it for Hess's law. I hope you are now feeling more confident in breaking down energy cycle and working with enthalpy changes. Don't forget to like,